All right, let's go over the quiz questions. Everybody has their paper, right? All right, let's look at number 1. And the code is, first we initialize I to 1. So I'm just going to type in the code here because I don't have it available right now.
Is the internet still down?
No.
It was down
On Monday.
2 minutes ago.
2 minutes ago.
Yeah. I'll try again. It feels down to me. All right. And so here we have a loop. So first we declare I, initialize it to 1. And then execution enters this loop, and there's a loop condition that I needs to be less than 64 to be true. So it's initially true. That means we go into the loop at least the first time. And so we'll see out I plus 1. Remember, keep in mind, this does not modify I. That does not modify I. It just uses I inside of an expression. For new people coming in, get your quiz from down here. Now this is where we modify I. And that's the confusing thing, right? This does not modify I. It just uses I in the context of an expression, which is, in that expression, evaluates to a value, which is then sent to cout into the standard output stream. But in the next line, we modify I. You see there's an assignment here. I is on the left-hand side of an assignment operation. So it's 2 times I. So what does this do? So the question is, what does it output to the console? Well, notice that the output operation is inside the loop. So we'll print something for every iteration of the loop.
You have 2 twos.
Thank you. There we go. So we just walk through it. So I is 1. 1 is less than 64. The loop condition is true. Then we have to evaluate this expression, I plus 1. Well, since I is 1, and I'm going to keep track of I down here. Here's my I, and I won't use an equal sign just to make sure I distinguish between the code we're reading and our sort of our note taking as we walk through the algorithm. So I is 1, so 1 is less than 64, so we'll compute I plus 1, which is 2. Very important, I does not change. So 2 is then sent into the standard output stream. So we print 2. And then the next thing we do is we evaluate 2 times I. This does not modify I. 2 times I doesn't modify I. It's the assignment here that modifies I. So 2 times I, which is 2 times 1, so that gives us 2. 2 is assigned into I. At that moment, we'll make a change to our note of what I equals at this particular time. Now we're at the bottom of the loop. What do? Well, we got to evaluate the loop condition. I is 2. 2 is less than 64. And therefore, we go to the next line. And we'll compute 2 plus 1, which is 3. Print it. By the way, we're also printing a space there. I put that in there so we would, just to get spaces between the digits, or the numbers. I did not change. We still, we don't even have to remember what I is because we're writing it down. So we don't have to burden ourselves with remembering what I is and forgetting about it because we're writing it down. All right, but we do have to remember what line we're on, and we're here. We just printed this. Now we'll do this statement. So 2 times I, well, I is 2, so that's 4. 4 is assigned into I. All right, so now I in that moment changes to 4. So we'll change our note about what I equals. Now we're at the bottom of the loop. So we got to evaluate the loop condition. I is still less than 64. So you can see here, I is being doubled each time. So I starts as 1, it's doubled to 2, it becomes 4, it becomes 8, it becomes 16, it becomes 32. You see it? This is the only place I changes. We can sort of drop what's going on here because there's no effect on what I becomes relative to the loop and the loop condition. So we know that I takes on the values 1, 2, 4, 8, 16, 32, 64. Because when I become 64 here, the loop condition is false. So we do not compute 64 plus 1. We do not compute 64 plus 1 because the loop condition is false and I is 64. So the iteration before that is when I is 32. So we do, when I takes on, we've already figured out that I will take on the value 32. If I is 32, the loop condition is true. And we print 32 plus 1, which is 33. So it's going to look like this, right? So each value that I takes on, which is 1, 2, 4, 8, like that, we just add 1 to it and print it. So 1 plus 1 is 2, 2 plus 1 is 3, 4 plus 1 is 5, 8 plus 1 is 9, 16 plus 1 is 17, and 32 plus 1 is 33. Now, the way I reasoned about the loop, but an easier way would have just been to keep track of what I is and just go through it one at a time. But if this value here were to be very large, then maybe it's better to do the reasoning rather than going through it manually. Okay, so that would be the answer right there. That's what it prints. What about the code in figure 2? New people coming in, your quiz paper is down here. So anybody who's just arriving, please get your quiz down here. So integer n equals -1. Integer k equals n plus plus times 3. So there's two statements. The second statement has got the post increment. And then we have a cout plus n times 9 plus k mod 4. What does it output to the console when it runs? Well, there's one cout operation here. When it's not a cout operation, it's one output operation to cout. So on this side, you know, we compute the thing that's on the inside. That's some value. We do mod 4. That returns, you know, modulo operation returns an integer. So we're going to print an integer. So that's what we're going to do. We're going to simply write down one integer. That's what this code does. It prints one thing. So we'll start with that kind of perspective. Now let's go back and walk through this. We only have 3 lines of code to evaluate. And we could do like what we did for 1, or we started to do for 1, is to keep track of the state of our variables. There's an n and there's a k. And that's it. There's only 2 variables. So the first thing we do is initialize n to -1. So n is -1. That's our record of what n is. K is not yet assigned. And then we do this. We have 3 operations: a multiplication, increment, and assignment. So you just have to know the order of these operations. The first thing we do is multiplication, because that's post-increment. So we do that at the very end. So n times 3, that's the expression, n times 3. Well, n is -1. -1 times 3 is -3. So This expression that I've highlighted evaluates to -3. It does not modify n, and it doesn't modify k. It's just a value that is computed from this expression. It's sitting in memory somewhere in the computer when it runs. Now the -3 then becomes the right-hand side of this assignment operator. So now k is being assigned -3. So k takes on -3. After this is all done, then we increment n. So -1, increment means +1. So -1 plus 1 is 0. And now what do? We're done with the second line. Let's go to the third line. So these parentheses tell us that we need to evaluate the expression inside the parentheses first before we perform the modulo operation. So let's evaluate what's inside the parentheses. Well, there's 3 operations. There's plus, there's multiplication, and then there's increment, the pre-increment, the one you do first. So let's do it. Let's do the pre-increment first. Let's increment n. N becomes 1. Now, after we've done this, then we'll do the multiplication. Multiplication has higher precedence than addition. So 1 times 9 is 9. We don't modify n. We're just computing the value of an expression. This increment here modifies n. So when we evaluated that, when we executed this operation, we're modifying n. It's also an expression, so not only does it modify n, but it also evaluates to the value of n after the modification happens. That's different than here. This expression evaluates to n, and then afterwards it's incremented. So this is now, n is now 1. 1 times 9 is 9. So that expression evaluates to 9. And then we add k. So 9 plus k. K is -3. We didn't have to remember it because we wrote it down. 9 plus -3 is 6. So this expression evaluates to 6. 6 mod 4. How many 4s do we take out of 6 before we can't take any more 4s out of it? 1. We take 1 4 out of 6. And we're left with 2. So the remainder of 6 divided by 4, the integer remainder is 2. So this expression here evaluates to 2. And that is the right-hand side of this output operator. So we print 2. And I'm going to clean up my work because they're just notes. Any questions? Okay, let's go to 3. Suppose that g is an integer variable. G is an integer variable. Write code that prints pass when g is greater than or equal to 60 and fail when g is strictly less than 60. So let's print pass when g is greater than or equal to 60. If g is greater than or equal to 60, let's print pass. And let it print fail when g is strictly less than 60. That's one way to do it. That's just like taking the problem statement and just directly coding it in my mind.
I didn't close it either.
What's that?
I didn't close my code and brace.
Here's another way to do it. forgot. No, that's okay. Because those two conditions, g greater than or equal to 60, is the opposite of g less than 60. So we could use an else expression here. We could do it like that. Any questions? No. Let's look at problem 4. When the code in figure 3 runs, what does it print? All right, let's look at that code. Integer k, 93. So we declare a k, initialize it to 93. Integer n, initialize n to 0. And then there's a for loop. The initialization section of the for loop, which runs once, the very beginning of the execution of the loop, is to declare an integer I and initialize it to 0. So we have 3 variables, k, n, and I right now. Then there's the loop condition. Which is I less than k. And then there's the end of loop operation, plus I. There's one statement inside the body of the loop. It's to increment n. You know, we could have done this, watch. This is equivalent to the following. It's also equivalent to this. So and it's also equivalent to this. These are all the same thing. So just something to keep in mind. But this is what the problem has. The problem shows it like that. All right. When this, after the loop finishes, then we have an output operation. So you can see the output operation is outside of the loop, which is different than that first problem that we looked at, in which the output operation was inside the loop. When the output operation is inside the loop, we repeat that activity of printing something. But here, the output operation follows the loop, and it's at the end of our code snippet. So we print one thing, and we're done. All right, so that's our high-level perspective of what's going to happen as we read through and analyze the code. I'll make it a little easier to look at by taking these out. So we have, I think I'm not going to keep track of variables. I'm not going to walk through this because I can see that the loop runs either 92, 93, or 94 times, right? So it looks somewhere around 93, roughly this loop runs, right? So we got to always keep in mind the off by 1 issue when we look at the code. So it's a lot of times. And so I'm not going to step through the code 92, 93, 94 times, adding 1 to n each time. So look at this. The loop starts at 0. And I takes on 0. And then the body of the loop runs. And then I takes on 1. And the loop runs. I takes on 2 and 3. As soon as I takes on k, we exit the loop. And we don't perform this operation. So when I takes on 93, we don't perform the statement inside the loop. So that means I takes on the values 0, 1, up to 92. Those values that I takes on, the body of the loop runs. But the last value that I takes on, which is 93, the body of the loop doesn't run. So that means this operation, this adding 1 to n, happens 93 times. The loop runs exactly 93 times. Maybe you have trouble understanding that. So what you can do is say, well, instead of 93, let's take, let's 2. let's analyze it with 2. I is 0, then it's 1. And then when it becomes 2, it doesn't do anything. So it just runs twice. It means we add 1 2 times. When we start at 0 and we add 1 2 times, we end up with 2. And, if we add 1 3 times, and starting at 0, we're going to end up with 3. If we add 1 93 times, we're going to end up with 93. So n, when the loop finishes, n is 93. So we compute the expression n plus 2, that's 95, and we print that. Any questions on that? That was, do I have my numbering wrong here? That should be 1, 2, 3. That's number 4, right? Oh yeah, so we're on number 5, okay. When the code in figure 4 runs, what does it output to the console? So let's look at that code. So integer I equals -5. So we declare an I, set it to -5. And then we have a while loop. While I is less than or equal to 695. I equals I plus 200. Once again, this output operation is outside of the loop, so we're going to run that only once. We're going to print one number. All right, there's only one variable. All we have to do is keep track of one variable. It starts at -5. Here, we initialize I to -5. The loop condition is true, so we add 200. So -5 plus 200 is 195. Now we check the loop condition. The loop condition is true. 195 is less than or equal to 695, so we add 200. So that means it's 395. Check the loop condition. The loop condition is true, so add 200. 595. The loop condition is true. Add another 200. 795. The loop condition is false. The loop is finished. We do not execute. We don't need to add 200. We don't execute the body of the loop. When I becomes 795, we don't execute the body of the loop. But we use I in the very last statement of the program. And so we send the value that I represents into the standard output stream. So we print 795. All right, let's look at 6. When the code runs in figure 5, what does it output? Let's take a look. So there's an integer I set to 1. There's an integer j set to 2. There's a double precision floating point number x set to 1.0. And then there's a following statement: cout I divided by j greater than 0 in parentheses. Then it's like endl here. Then there's another one: cout x divided by j greater than 0. It's the same expression. So we have 3 variables. And the value of those variables do not change in the program. All we need to do is carry out these two statements. That's the first of the two statements. So look at this. Look at all the operations in here. Remember, we have to figure out what operation do we do first. Let's see, how many operations are there? There's an output operation here. There's a comparison operation here. A division operation here. Oh, what kind of division? Is that integer division or floating point division? It's integer division because I and j are both declared as ints. So the compiler sees that operation as integer division, but look, it sees this operator as different. It's a different operation. That's floating point division. It looks like the same symbol. It is the same symbol, but it has a different meaning. Its meaning comes from its context. So you can see that the numerator is a floating point variable, and therefore the compiler interprets that slash character as floating point division. So 1, 2, 3, 4. There's 4 operations in each of these expressions. And so which one do we do first? Well, these parentheses tell the compiler to perform this operation first. And then the result of this will be this value, whatever this evaluates to, that value will be sent into the standard output stream. Because this output operator runs next. Now, this expression that I've highlighted, exactly highlighted right there, that expression results in some value being sent into the output stream, but that expression itself also evaluates to something. What does it evaluate to? Who knows this? What's that?
False.
No.
Zero.
No. You got to get this.
The actual value or what's the
No, in the execution of the code, in the execution of the program, what I have highlighted exactly evaluates to something. What does it, because look, this, what I have highlighted, is the left-hand side of the second output operator. We're certainly not going to evaluate to 0 because it doesn't make sense. It's not an output stream. 0 is not an output stream. This operation is meaningless if the left-hand side evaluates to a number.
0 is greater than 0.
Huh?
0 is greater than 0.
0 is greater. No. This is the left-hand side. Look, this is the operation. This operation has a right-hand side, which is the value that's sent into the output stream. And the left-hand side is an output stream. The left-hand side of this output operator must be an output stream. It has to evaluate to an output stream. Otherwise, the compiler won't compile it. So which output stream does it evaluate to? The standard output stream, otherwise known as Cout. What I have highlighted here evaluates to, gets replaced by, becomes Cout, which then functions as the left-hand side of that second output operation. How many people get that now? I've repeated this many times. No, not one of you got it yet. You got to get this. This is how you read code, okay? I'm showing you how to read the code. So this expression evaluates, in general, this output operator. When this output operator runs, when it executes, it returns, it evaluates to the left-hand side. So whatever you had, if you had S out over here, then this expression would evaluate to S out. That's all. And that's the reason why you can cascade these things, see, one after another. Because each time, the evaluation is left to right. So when the first one runs, when the first output operation runs, it evaluates to its own left-hand side, which then functions as the left-hand side of the next output operation. So you can have any number of these output operations one after another. And that's the reason they designed it like that, the language. Okay. All right, now the next hard part. What's the data type of this expression? Is it a string? Is it a character? Is it a float? Is it a floating point value? Is it a Boolean? It's a Boolean. It's a Boolean because of this operation. There are two operations inside the parentheses. There's division and there is comparison, greater than comparison. The division has higher precedence. I is divided by j first. This sub-expression evaluates first. What does I divided by j? What does I divided by j evaluate to in this code? It's integer division. I is 1, j is 2. It's 0. That evaluates to 0. This 0 becomes the right-hand side of a comparison operation. 0 greater than 0. You see? 0 greater than 0. That's an expression. 0 greater than 0 evaluates to either true or false because it's a comparison. Is it true or false that 0 is greater than 0?
False.
Is false. So this whole expression evaluates to false. And that false becomes the right-hand side of this output operation. The false is sent to the standard output stream C out. So we print false. After we print false, this whole expression evaluates to C out, as we already explained. And so we send a new line character into the output stream. So, the next thing we print is down here. All right, the next one, x divided by j is what? Here. This is floating point division, so it's 0.5, that's right. Is 0.5 greater than 0? Is true. So this expression evaluates to true, and we send true into the output stream. So true gets sent into the output stream. I mean, true is displayed on our console. And then this expression evaluates a C out, which becomes the left-hand side of the second output operation here. So we just print another new line, which doesn't really matter that much in our context. So false and then true. All right, the purpose of these exercises and what we're doing right now in the course is just learning how to read the code. And that's why I'm going really slowly over the small steps of how to look at and understand each of the symbols you're staring at. All right, number 7. What does this print to the console? Integer I equals 4. So I is declared initialized to 4. Then there's a for loop. K is initialized to 0. The initialization step, we define a K, initialize it to 0. Then the loop condition is that K is strictly less than 300. And then the end of loop operation is to increment K. What do we do inside the loop? I equals I plus 3. And when the loop finishes, we have an output operation with the variable I. So there's two variables to keep track of here, I and K. So K starts at 0 and is incremented here. That's the only place that K is modified. It's initialized to 0 and it's incremented at the bottom of the loop. And this is a constant here, so K less than 300. So we can see, just by looking at this, how many times the loop runs.
300.
300 times. 300 times exactly. Not 299, not 301. Because we start at 0, we do the loop. We go to 1, we do the body of the loop. We go to 299, we do the body of the loop. We hit 300, we do not do the body of the loop. So we stop, we do not execute this line when K becomes 300. On the other hand, we started from 0. So from 0 to 299, that's 300 times we ran the loop. This loop runs exactly 300 times. And if you can't remember all that stuff when you're taking the exam, then just say, well, instead of 300, let me just throw in a 3 or a 2 and figure it out from there. And then you can, what's the word? What's the verb? Once you look at the simpler case, you can project what the answer would be if you use 300 instead of a smaller number.
2 times 3.
So, oh, deduce. I think that's the word I'm looking at. You can deduce. You can deduce the number of times the loop runs when you use a larger number by looking at cases where you're using a smaller number. Okay. All right, so I starts at 4 and you add 300 times. So what does I end up being when the loop terminates?
904.
So 304.
304?
I'm sorry, 904. Yeah. Write code that prints 300 random integers that are less than 2,000. We need to print 300 random integers that are less than 2,000. Hey, wait, there's 2 parts. We got to do something 300 times. Let's just forget about the something. I know I got to do something 300 times. All right? We just looked at this loop, how to do something. Huh? Actually, I just copied that. This is a loop that does something exactly 300 times.
You skipped the question.
That's
Yeah.
9.
Oh,
That's number 9.
oh, that's 9. I'm sorry. That's 9. Let's do 9 because it's related to, and then I'll go back and do 8. 9, print 300 random integers that are less than 2,000. So you see the loop? We have to do something 300 times. This is how you do something 300 times. All right. And let's print random integers. Well, let's just print one random integer, just some random integer. We don't need that. I'll just take that out. But rand returns a random integer between 0 and the largest positive integer value. We want to constrain the result so that it's between 0 and 2,000. So the trick is to use modulo. So we just do rand mod 2000. All right, that's that.
Oh my god, I wrote 200 instead of 2,000.
So the random value, see, we divide by 2,000, take the remainder. That'll give us a number between 0 and 1,999. That's it. It gives us the random value that's less than 2,000. That's what we want. All right, number 8. So it's, what does the following code print? Let's look at that code. Clear this out of the way. So declare I, set it to 0, 2 rather. Declare K, set it to 7. And then execute a while loop. The expression, the loop condition is I is less than 214. And there are 2 statements inside the body of this loop. The first statement assigns something to K. And K gets whatever K is minus 3. And then the next statement is to assign I times 2 to I. And then at the very end, we output K. So as you can see, the output operation is on the outside of the loop. We're going to print one thing. That's our high-level view of what's happening here. So we have to figure out what it is we print. What does K become after we complete the execution of that while loop?
Here becomes negative. Four.
Well, here, take a look here. Here, the loop condition depends on I. So we just want to see, well, how many times does the loop run? See, each time the loop runs, we're concerned about ultimately what K becomes. And the loop decreases K by 3. So if we know how many times the loop runs, if the loop runs twice, then K will be reduced by 6. That's 2, subtracting 3 2 times. So let's focus on understanding how many times the loop runs. Well, I is initialized at 2. The loop condition depends only on I.
It's going to run 7 times, I believe.
It's going to run 7 times. Why does it run 7 times?
Because you're doubling every single time. So first you start off with I being 2,
Yeah,
and then it's going to be 4. So it's going to be 4.
So I starts off at 2, then it's doubled to 4.
Then it doubles to 8, 16, 32, 64. And then when it gets to the 256, it tests the condition but doesn't run.
So that's when it becomes false, right? The condition. So the body of the loop will not run
Yes.
at 256, but it will run for these values.
C.
So how many times does the loop run? 1?
7.
Well, you said 7, right?
Yeah.
Okay, I'm not going to add them up, but there's 7 values that I takes on. And for those 7 values that I takes on, this statement here runs. So we're going to subtract 3 7 times.
So you're going to take, what is that?
So-
Negative 21 minus, or plus
Minus
7.
21, 7 minus 21.
Yeah, so it's negative 14.
7 minus 21, what's that?
Negative 14.
One more to go.
I still dispute it. Still dispute it.
You dispute that one? Oh,
It was very misleading.
Oh, yeah. I guess you would call that a trick question.
Are you
Okay.
admitting to that? Because I mean, I'm just saying.
No, it's just what it is. I'm trying to debug your mind so that you know how to read code. So I gave you problems that are going to, that you're going to miss, okay, on purpose. Some of the problems are easier than the others.
We should take a vote. I'm just saying.
Take a vote.
I'll let you know if we're doing it.
So let's do 10. Write code that computes the sum of integers 100 through n, inclusive. That means include 100 and include n. So if n were 102, we would compute 100 plus 101 plus 102, right? That's what inclusive means. So write code that computes that sum where n is an integer strictly greater than 100. So n cannot be 100, but n can be 101. It's given. N is given. So, you know, there's, we want to compute the sum of values. So 100 plus 101 plus 102, and we want to include n. So that's what we're computing. I should have made this larger. Sorry about that. Okay. So, as usual, there are a number of different ways of doing this. And I'm just going to get started. Well, there's going to be, look, these are values. We need to look at 100. We need to look at 101. So do you see that this is like the index? This is an integer inside of a looping condition. So integer I equals 100. We're going to start at 100. We're not going to start at 0. I is less than or equal to n. And then increment I. So here we need to compute the sum. We're adding these i's together. So is some variable, say it's sum or x, whatever. And we want to take what's in there now and add the current I to it. So we need to declare an integer sum, initialize it to 0. There we go.
Don't we technically need to declare n as well?
No, well, you can if you like, but I've in the in the problem statement, I'm saying that n is a given. It's already, I say it's an integer, so you just use n.
Okay.
I'm just after that. I just want to see that you can get this algorithm here. Yeah, I don't care about the cin and all that. You know, I didn't really ask for user input here. Just n exists. It's an integer, and it's strictly greater than 100. You can assume that, and now write the code.
That's why you got 5 points.
No, I want to. Here's another problem that almost always appears, and it's compute the average. What's the average number? Well, no, that's not a good. Maybe I'll wait. I'll do that one later. You need to have vectors for that. All right. Okay, I think that's enough for today, right? Okay, we have lab today, and is there any other comments or questions? No? Okay.
Can you do number 4
I thought I did number 4
on the
already.
lab?
Oh, do you want to do that? We can do that.
Can you
you
go
can do that.
over the
Yeah.
lab? Because like, I
Yeah,
don't know,
sure.
I mean,
Or if you want to just code it and then just explain it, so like
Yeah.
get the code, that's also cool too.
Oh, we have 15 minutes, right? Oh, so if you want to leave, go ahead and leave, but we'll keep working. So
Or maybe could you
let's.
explain functions to us?
Oh, functions, yeah.
On a side note, how do you randomize a number in a function?
This is called rand.
Yeah, but it's not working. I'll show you in a second.
Which one do you want to look at? One?
Let's go 1.
Let me, because we only have 15 minutes, so.
It's lab number 4.
functions.
Look at that. Give me a second, I can get that going. So hold on.
Now it's say universe San Bernardino dt or San Bernardino dt dot github dot io/201-2014 -fall/l4 dot
Oops. Must be 4,000. All right, functions.
Implement a function that takes an integer value.
Oh yeah, so functions. So we already have this code, right? Which
Yeah.
problem? Which lab is it from?
Isn't that like Larry?
Lab 3,
That's 4.
exercise
One.
Exercise
1.
Lab 4, not lab 3.
Now where do,
Exercise 1.
which?
Oh.
Yeah, thank you. So this is the code that decides whether the value inputted by the user is prime or not. And so what we want to do is use function. We're going to refactor the code. We're going to reorganize the code so that it uses a function and make it hopefully easier to look at the code, to understand it, and to grow it, to use it in a larger program. So the function that I specified, the function should look like this. So it's a Boolean value, it is prime, it takes an integer and it returns a bool. So I'll list that function up here. So when we call this function is prime, we're going to pass in an integer value, and it's going to return true or false. It'll return true if it's prime, it'll return false if it's not prime. This is called a stub. I'm just returning true all the time. So it's an incorrect implementation, but just to get the general overview understood and coded, I'm going to use a stub. Yes?
So in C++, when you're using booleans, is it always going to be true, false, or is it going to be 0, 1, or is it interchangeable?
It's interchangeable.
Okay.
Yeah. In other languages, it is not interchangeable. In C++,
And I was round and round about that the other day.
Yeah.
It's like, well, I don't know if it's always going to be 0, 1. I said, well, I know in this case, the professor said it will return true, false, but then when we were coding, I did true, he did, like I was doing true, false, and he was doing 0, 1.
yeah, well, that would be considered bad form to use 0 and 1. But it's the way things used to be done. And I think the predominant style now and opinion is it's better to use true and false. It's more expressive. It's easier to read. Okay. So let's look at, let's just pretend that this function, we call it, we invoke it, it returns true or false. Just lets us know whether n is prime or not. And we're going to keep a lot of our original code. Here we declare an n, we ask the user to enter an integer greater than 1. We read in the value into n. And here we have code that looks for a divisor. I'm going to comment this out with a multi-line comment. See that? This is the closing comment. This is the opening comment. So this chunk of code will end up going inside the function, but just for now I'm going to leave it out. On here, if we found a divisor for n, then we print it's not prime. But now what we're going to do is we're going to call the function is prime, passing in n. And this function returns true or false. So this expression right here that I've highlighted, that's an expression. It's a simple expression. It just calls a function and it evaluates to true or false. So that's true or false is an acceptable value to use inside of an if statement, the if condition. So when we call the function, it returns true. When it returns true, we're going to print that n is prime. So I'm going to change this a little here. So when is prime returns true, we're going to print it is prime. Otherwise, we'll print it is not prime. See that? that compiles 4. 4 is prime. So we've got that running. This doesn't run correctly. Form is not prime.
Yeah.
But that's because we're using a stub, right? We're just getting the shell to work here. This is called a stub. I've repeated that about 20 times already, so I want you to remember that word, okay? It's the purpose of my repetition. It's not because I'm getting old, which is also the case. But now this code here is our old code, which takes a value, n, and decides whether n is prime or not prime. So let's take that code here. And paste it into our function. Yeah, I'm going to get rid of this section here.
What would you do if you put the function at the end of the program instead?
I'll do that next. That's a good question. Remind me when I get finished to do that. Okay?
Prototypes.
Yeah. Thank you for asking that. So found a divisor for n is false. Now we go through the loop, and if we found a divisor for n, we set it to true here. So now instead of returning, well, there's a number of ways that we could do this. Let me show you the easiest way. Here, inside here, if at this point, if we find a value I that divides evenly into n, at that moment we know that n is not prime. So let's go ahead and return false right in that instant. We don't need this code. We found the n, we found the I rather, divides evenly into n and can't be prime. Let's return false. We know it right there. But suppose it goes through the loop and we never return false. That means we checked every I. We didn't find an I that divides into n. So let's return true. It must be prime. You say, actually, it simplifies quite a bit here, doesn't it? We don't need that intermediate variable, which is this one here, so I'm going to take that out. Look at how much simpler that is. And then we have this logic, nice, in a compact form. It's tucked away, it's, boxed into this function, this, input, output sort of box. And we can invoke it inside of our main code down here.
Since up there we have kind of like the if and mod I is 0 return false.
Yeah.
Would we also need the else or no?
No. Because you have to try every n. You can't return true until you've tried every single n. Every I. You got to look. You got to check every value less than n to see if you can find a divisor. If you find one divisor, you know it's false. But if you don't find a divisor, the first divisor you're going to try is 2, because I starts at 2.
Mm-hmm.
Well, let's suppose that, let's suppose we had like 9. And, 2 doesn't divide evenly into 9. So, that means we'll return true. No, because we've got to try 3 next. So if you put an else here, then you're not going to run the loop. You're only going to run the loop once. Because you will always either do this or that. So you'll always return after the first iteration of the loop. So you cannot conclude that it's prime by looking at just 2. That means it's even. But 9 will return true for 9, but 9 is not prime. Is that okay, everybody? All right. But this is a common mistake. So it's very good to have asked that and to look at that. That's a very common mistake that students make. There's another question about functions, the place in which you list the functions. We could define the function below main. Like this, okay? Maybe we like it. Maybe we feel that that's more readable. But watch, this will not compile. Use of undeclared identifier is prime. So the compiler, look at how the compiler is working. It's interpreting the code sequentially. So when it gets to here, it says, oh, I got to call a function named is prime, but hey, wait a minute. I don't know any such function. That's because we tell the compiler later on about the function is prime. So at this point where we're using it, the compiler says, I don't know what that is. So the compiler works sequentially. So what we can do, because this organization is a common organization, we'd like to list the details later. I mean, that's just, it's what your preference is on that one. So we can do what's called a forward declaration. We can tell the compiler that is prime, the name is prime, is a function that returns a bool and takes a single argument that's an integer. And then we put a semicolon here without the braces, or without a statement, to tell the compiler, without the braces rather, to tell the compiler this is just a declaration, it's not a definition. So there's two words here, declaration, definition. When you declare a name, a variable or a function, you're telling the compiler that about the name, the data type of the name. What does the name represent? What kind of a thing? But it doesn't tell the compiler how to build this thing. It doesn't have an initialization to it. Doesn't show implementation for the function. So here is the function definition. Here is the function declaration. Yeah.
Can you feed in more than one argument?
Yeah, you can have more than one argument, but we don't need that in this case. So if we want another argument, we could do like this. Sorry. Let's just check that works. That works. That's the overview on functions.
Four.
Generate a web page.
Can we do that in lab?
Yeah, we can do this in lab.
I'm gonna be at lab then.
Yeah. This is, this is very similar to the last lab, right? Most of these problems are revisions, a variation on the problems that I gave you in the previous lab. Okay, I think that's enough for today. I can present these in lab as needed.
So are we just pushing our output into the web page then for that one since we're generating the web colors again?
Just send the output to cout.
Okay.
And then you'll use the use the redirection operator down here on the command line to send, to declare the standard output stream, to redirect standard output stream to a file. That's the very last line.